This presentation is to give you an introduction to the framework of models and data that went into the project called Enhancing the Climate Resilience of African Infrastructure, which was performed by the World Bank and the African Climate Policy Center of the UN Economic Commission for Africa, funded by the agencies that you see at the bottom of this first slide. The objectives of ECRAI were to strengthen the analytical base for investment in Africa's infrastructure under a future uncertain climate. As we approach anthropogenic greenhouse gas emissions and a changing climate, there are a number of issues that we face in bringing this potential climate change into the realm of design and planning of infrastructure, and in particular for Africa, where the uncertainty of the future climate is even greater than many parts of the world. So there are three main activities related to this project. One was we wanted to estimate the impacts of climate change on the performance of a subset of infrastructures over a range of climate scenarios. Here, basing our work on NAPAD, we wanted to look at what infrastructure is planned in the immediate to mid-range future and see how vulnerable these infrastructure investments would be to a changing climate over their lifetime. As we did this, we wanted to develop a framework that could be used by planners and designers as they looked at other infrastructure that may not have been in the range of projects that we examined, so they too could look at a robust solution to how to design and plan for a changing climate and produce what we have been calling robust solutions that deal with the risk of an uncertain future. And then finally, we want to enhance the investment readiness of African countries to get access to climate finance to help make their projects more resilient, which will require that there be analytical analyses carried out on specific projects to look at their vulnerability and potential adaptations to climate change. In doing this work, as we said, we were looking at both planning and design. As we looked at planning, we took a large-scale approach. We looked at 7 major river basins in Africa because the 2 major infrastructures that were being focused on here was hydropower development, which is an important priority to Africa in a path of green energy development and low carbon energy, particularly electricity, and also looking at irrigation and providing food security for Africa. So this would occur at the basin level and would require the issue of looking at planning. Additionally, these basins, as can be seen on this map, are all transboundary river basins that span the borders or cross borders of at least one or more nation. This adds to the regional and cooperative nature of climate change impacts and adaptations that should be addressed. So we have looked at the Upper Orange River, which includes Lesotho and South Africa. We've looked at the Zambezi River, which includes Namibia, parts of Namibia, parts of Angola, Zambia, Mozambique, Zimbabwe, Malawi as well. The Congo Basin, which includes both the Democratic Republic of Congo and the Central African Republic and parts of Congo itself. We have the Nile Basin, which includes the 11 countries and falls into 2 parts, the Equatorial Lakes region on the equator, and then the Eastern Nile, which is Ethiopia, Sudan, and Egypt. We then have also looked at the Niger River Basin in West Africa, which interestingly spans horizontally from across the Sahel regions, emptying out into Nigeria. Also, within the arc of the Niger Basin is the Volta Basin, which is draining from Burkina Faso, a little bit of Nile, a little bit of Togo, and then into Ghana. And then finally, we looked at the Senegal River, which rises primarily in Mali, drains into Senegal and parts of Mauritania. So looking at all of these hydropower, we were quite interested in how the hydropower would be developed in each of these, but we wanted to take the bigger look and see how does this fit within the energy picture of Africa. So in particular, there was a study. In this study, we looked at the existing and potential future power pools of Africa. And here, the hydropower would be analyzed within the light of other energy sources. And we looked at 4 of the 5 major power pools of Africa, which are the Comelect, which is the North African power pool. Then there is the East African power pool, the West African power pool, the Central African power pool, and then finally the Southern African power pool. Each of these operate within their countries and then trade within those countries. And we looked at how hydropower and the impact of climate change on these potential hydropower generations might affect the cost of providing electricity in each of these power pools, with the ability to trade within the power pools and without. So while we look at large-scale river basins, we also then looked at project scale, because project scale is where funding and loans will take place in development banks. And so as we look at this, we looked at what we call track 2 in this analysis, track 1 being the river basins, track 2 being project case studies. And we looked at 5 case studies. Number 1, right in the central part of Africa flowing into the Zambezi Basin, was the Lower Fufu hydropower project in Malawi. We then also have in the Orange River Basin, the Polahali, which is actually in the country of Lesotho, which is involved with both supplemental water to the Orange system, hydropower generation, and then also water transfers. We look at the Palugo project in the Volta Basin in Ghana, just below the border with Burkina Faso, and there this is irrigation and hydropower. Finally, we looked at the Batoka Gorge project, right below Victoria Falls on the Zambezi River and above Lake Kariba, which is a hydropower project. And finally, in Kenya, we looked at the Mwache Dam, which is part of a water supply for municipal and industrial use, and how that would take place. So we wanted to look at how does climate affect these specific projects, their design in particular, and what is the risks of costs to that, and what are the adaptations that may be economically feasible as we look at these projects on a one-by-one basis. How did we do this analysis? The way we did this analysis was in 4 steps. First of all, we had to come up with a reference case. So that is, what is the base plans that are there by the countries and the river basins for infrastructure development up to the year 2030 in terms of future megawatts planned, hectares of irrigation to be developed. We looked at that with the current climate as a baseline. We then looked at in step B what would be the impacts of this by looking over 100 future climate scenarios, and that come from the uncertainty of both emissions of the future as well as the scientific uncertainty that comes from the different climate models. We assumed a very static condition, that there would be no adaptation. So this is, if we do not act at all, the potential vulnerability of these projects to the impacts of climate. We then went and used a technique called perfect foresight adaptation, where if we assumed we knew the climate would come, how would we modify our plans? So for each of those 100 projects, if we did know that this was the future climate that was going to come, what would be the design that we would do to adapt to either too little water or more water than we thought. And then finally, we talked about robust adaptation. This is a decision methodology that has been developed, known as robust decision making, that assists policymakers in how to select design alternatives in the face of uncertainty. And in our particular case, the over 100 future climate provides quite a range of the future, which makes the future uncertain. So what action should policymakers take and designers take at the track 2 level, and at the planning level in track 1, what should we do? So taking those 4 steps, we had an analytical approach to do this. So finally, what did that mean? To do this analysis that was needed for the robust decision making, we had to have data and tools. So this activity that was taking place spent a lot of time to gather the data. That data included the reference climate data for Africa on a gridded scale that was appropriate for our river basins, the climate futures, which come from the what's called CMIP3 and CMIP5, the climate community, their models of what the future climates would be under different emission scenarios. There was then how will Africa develop in the hydropower and irrigation infrastructure, looking at the PETA primary projects and then what we called PETA Plus, which were local national plans that go along with the PETA, which are international transboundary activities that the PETA project has identified. And then finally, working on what is the economic growth and the energy demand that will take place that will cause the demands for the electricity and other activities that are going on in the basin. So with this, we used three modeling activities. One was a water model, which was known as WEEP, Water Evaluation and Planning Tool, developed by the Stockholm Environment Institute. And then an energy model for looking at the electric system, which is known as osmosis, developed by an international team, but led by Mark Harles from the Royal Institute of Technology in Stockholm. We then were able to run these models in a wide range of activities to look at impacts, to look at adaptations, and also to look at robust decision making. The following sessions that you will see in these different video vignettes will talk about the different components that are in this framework, which I've just identified on this last slide. So this is an overview. The details of this is in the report that was published by the World Bank on this in both its main text and in the technical appendices that go along.